Hello, this is David Huter. Welcome back to my series on mathematical modeling of the coronavirus outbreak. Today we're going to look at the effect of asymptomatics, as I promised yesterday. So, we're going to describe the trajectory of a person throughout the disease states during the course of the disease. So the person starts out susceptible, then becomes asymptomatic, infected and asymptomatic. That is to say, they don't have any symptoms. You can't tell they have the disease, but they do have the virus in them, and in fact, they can spread the disease. Then they're infective, which means they do have symptoms. In this model, they have symptoms and they're spreading the disease. And then they recover and become immune to the disease. Now, the dynamics that we have here, as we've seen in models in the past few videos, births will be susceptible, so we don't have newborns who are in any of the other disease states. All of the states will have deaths. The only different death that we've taken here is for the infectives. We're presuming in our model that susceptibles, asymptomatics, and removed immune people all will have the same death rate. Then we have interactions of asymptomatics with susceptibles that will produce a new case by rate of lambda 1. We have an interaction of susceptibles with infecteds that will produce new cases at a rate of lambda 2. We're presuming that everyone goes first into the asymptomatic stage for some length of time and then goes into the infective stage. So the rate of change from A to I is gamma, which means that 1 over gamma is the length of time that they spend in the asymptomatic state. And then people recover from the disease at the rate of rho, as we've seen in the other videos. So 1 over rho is the length of time in the infectious class. So this is a diagram of the model that we're going to look at. Let's go down to the class note. As we've seen in the previous videos and in class notes, here we have basic definitions of susceptible and removed. They don't change. Asymptomatics are people who have been infected, but does not yet show symptoms, but they do produce new cases. Infectives, in our model, have to be symptomatic, and they are transmitting the diseases until they are removed by containment or recovery. So the rates that we just talked about in the diagram there, lambda 1 is the number of contacts per unit time that a typical asymptomatic person will make. Those are contacts adequate to transmit the disease if the person contacted is susceptible. Lambda 2 is the number of contacts per unit time for symptomatic people. And then the rate of change from asymptomatic to symptomatic, births, deaths due to the disease, with the recovery rate from the disease. So those are our parameters that we have to estimate. The model, as we did before, we have fractions A or S. A are of the population. These are fractions of people in each of the cases, fractions of the population. N is the number of people in the population. So our time unit here is days. In the first video we looked at weeks, but this one is days. So the number of people changes per unit time, number of susceptibles. They're lost by interaction with asymptomatics, and those people go down into the asymptomatic group. There's an interaction with infectives, and those people become asymptomatic. Their births, their deaths, and then in the asymptomatic group, there are also deaths, and then people becoming symptomatic. In the symptomatic group, then, we have people coming down from the asymptomatic, the gammas. Then we have deaths due to the disease or death rate influenced by the disease, and recovery rate rho. Those people who recover go into the removed class, and then there are deaths from the removed class. If we add all these up like we did the last time and divide by n, we get this expression for n prime over n. Notice that on the right there's no n involved. So when we do the arithmetic with the product rule that we talked about before, and we divide by n, we get the equations that we had before without the n's, but we have to subtract this term for each one of these equations here, as we saw in the first video. So eliminating the n prime over n by replacing by this particular expression here, we get the system of equations that we're actually going to program and estimate the parameters for. So let's go over to the program. The first thing I did is to validate the program. These are the usual functions that we can use to recall the definitions of things and the system of equations that we're dealing with. If you type print DE with parentheses, empty parentheses after that, in R, once this is run, you'll be able to see the equations as we've programmed them. These are the parameters that we're using. So here's how I selected these parameters. The beta and delta I left in our previous models. The lambda 1 and lambda 2 I selected in this validation program. This program I used in the following way. There was a Lancet study that says that the infectious period after symptom onset is 20 days. So that's 1 over 20 or 0.05 would be a rho value. So I changed that rho value there, and I had to have a delta D value. How do I pick my death rate due to disease, and how do I pick these contract rates between the asymptomatics, lambda 1, and the symptomatics, lambda 2, and the susceptible populations? I wanted to validate this by looking at the actual data for the country of France, the number of cases, and the number of deaths. So I ran this validation program here. If I start here and go down, this is the same program we've seen in the other videos, but the model has been changed, but the approach is the same. So I've got all of my deaths up to day 25 of the coronavirus, and I can copy that, and let me go over to R and paste it in. And what this gives me now are the number of cases. The red curve is the number of observed cases, and the blue curve is the number of predicted cases using our model. So that for simply the number of cases, using let me go back to the program here, using the values in my parameters here, 0.269, 0.269. Remember from yesterday was 0.285, and I'm adjusting this so that we can reproduce with all the parameters initially set, we can reproduce the growth curve of the disease. And now I have to select my delta for death to match the number of deaths observed in the population. So I'm going to go down here at this point and block out the plotting of the cases. And now if I copy all of this, after that, as we did in the last video, we looked at how many accumulated deaths we have in the course of the disease. So I'm going to go back, mark all of this as before, and plug into R again. That will give me now this new curve is the observed deaths are the red curve, and the blue curve are the theoretical deaths predicted by our model with the parameters that we've selected here. So, and let's go back to the program that I used. This is a copy of the program, except this particular program goes further than the first 25 days. Our validation that we just did looked at the number of cases and the number of deaths up to day 25. And we saw that with these parameters fixed in the way they are, we have a good fit between the number of cases observed and the number of deaths observed. So that gives me confidence that these parameters are in some way realistic. So now notice that I fixed my lambdas the same, and this is for days 1 through 25. So if I go down here later, after day 25, from day 25 till day 200, I'm going to run the program again with the same values, but now I can select the lambda 1 and the lambda 2. Now what I did in the first few runs is I left the 269 in there for lambda 1. So my asymptomatic people would continue to interact and spread the disease in the same way that they always have. And just to see what's happening in the whole curve, if I didn't have any influence whatsoever, I could leave the 0.269 in there like that and go down here, and in my title I've started with lambda 1 as 0.269, and I've not done anything after day 25. So there I can copy this and paste it into R again to see what this predicts for my whole history between days 0 and day 200. So I can see, as we saw yesterday in the curve, that I've reproduced the curve, this tremendous outbreak that goes up to over 30 million cases in the course of the disease. I have variables y1 and y2. Y1 is the number of infectives, so that's 30 million. It goes up to 30 million, the red curve. The blue curve values are called the y2s, and it's 9 million. But since we have symptomatic and asymptomatic cases here, this is just the curve of what you see. So these are just the number of infectives, people who are symptomatic. We need to have an idea of how many cases we have. So those are the symptomatic plus the asymptomatic. So those are called cases here. So I can look at my maximum number of cases, and this is in the program. And the maximum number of cases is actually 46.7 million cases. So I have 30 million infectives, but another 16 million asymptomatic cases. So the important thing is I can't get rid of the disease until I get rid of the asymptomatic case. So let's go back one more time to our program and to see what kinds of runs I've made with the program. I left the first part the same. So I said, well, we're going to go on to day 25. The disease is going to start to spread. I have a certain contact rate, lambda 1 and lambda 2, and I don't intervene until day 25. And then I have a declaration of confinement, or I have an encouragement of social distancing. And so then I go down to the second part, and the lambda 1s, this is the contact rate for the asymptomatic people who don't have any symptoms. So I can cut my symptomatic ones. They're the ones that I can confine or make them stay at home. I would like to reduce the asymptomatic ones as well, but suppose I don't. Suppose I just have some kind of way of containing the symptomatic cases because I haven't tested everybody and I don't know who is asymptomatic. So that gives me dropping down to 0.135. I'm just cutting this in half, 0.135. So here I've started out at 0.269, and at day 35 I dropped that lambda 2 down to 0.135. So I'm going to run this. I'm going to mark that, copy it into R, and we'll see what happens for the full time. This is what we can see here now. If we look at max of Y1 and max of Y2 and the max of my cases, then I have 27 million infectives. So it looks like I've dropped down from 46 to 27. I have 9 million deaths. I have 40 million cases because of my asymptomatic patients. So let's go back to the class notes. I ran this several times, and here are the results of changing lambda from 0.269 at day 25. Here in the first three runs, I left my lambda 1 at 0.269, so I don't detect my asymptomatic cases, and I try at day 25 to reduce my symptomatic patients. I start preventing them from circulating, and notice that I don't really reduce the number of cases that much. I mean, I do reduce the number of cases, but my reduction in number of deaths is minimal. So what happens is we have to either test everybody or test a good sample so that we know who's asymptomatic and who's not, or I have a general containment sort of, or confinement or social distancing program, which is what we started. If the social distancing program only works on the symptomatic cases, then I'm not going to really make much of an effect. Notice here, in my social distancing program in the last run, I've reduced the activity of the asymptomatic people as well. So I can see a much more marked effect on the cases. I've even brought my total cases down to 19 million. But I haven't really reduced my deaths that much. And remember that yesterday, when we had only symptomatic infectives, we did not have asymptomatics. When we dropped down to 0.07, we actually killed the disease. So what's going on here is that the asymptomatic people are responsible for maintaining the disease in the population. So the conclusion here is that you should, sometime when the tests are available, you should actually be testing everyone to find out how it is. You might identify asymptomatic cases, but still, the bottom line, social distancing, if you can stop everybody, not just the infectives, but also the asymptomatic infectives, if you can stop everybody from circulating around, then you'll be able to have an effect on the disease. And so, as usual, I will give you these class notes programs, the PowerPoint slides, and you can play around with this Lambda 1 and see what happens when you take that down to lower levels. Thank you very much. I hope you enjoyed this, and I'll see you in another video.